The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone, and thank you for joining our webinar today. My name is Carrie Williams, and I am the Director of Marketing for TestOil. I'm very pleased to host this webinar today. Before we get started, there are a few housekeeping things I need to take care of. First, I need to check if my audio is working. So if you can hear me, can you please click on the little hand icon on the GoToMeeting toolbar that should be probably on the right. Okay, I see Tim and Ron raise their hand. So it looks like people can hear me. That's great. Now, everybody is going to be on mute throughout the course of this webinar. We have more than 100 people registered, and I'm recording the webinar so I can share it with you and others later. So to make sure I have a nice, clean, high-quality recording, I have to keep everyone on mute. Now, if you have any questions, you can submit your questions using that same toolbar. There's a question section. Go ahead and type your questions in there, and if there's a good breaking point, I can jump in and interrupt the speaker. I will ask the question for you, but in most cases, we save the questions till the end of the webinar. So feel free to, throughout the course of the webinar, to type in your questions, and then I'll present them to our speaker at the end. So let's go ahead and get started. Our webinar today is titled Interpreting Additive and Contaminant Report Results in Oil Analysis Tests. Our speaker today is our Senior Technical Advisor. He's actually our lead trainer. His name is Evan Zabowski. Evan has more than 20 years experience in the industry, most of that time spent as a professional instructor. He is a CLS certified. He also holds many other certifications. He, for the past 8 years, has been the editor of TLT magazine, which is an STLE publication, and he's been working with TestOil for almost coming up on a year now. We're very happy to have him. And with that, I'm going to go ahead and turn everything over to Evan. Are you there, Evan?
Great. Thanks, Gary. Today's presentation is kind of a carryover from the previous webinar that we hosted, but for those of us joining today for the first time, let me go over a few fundamental things about our analysis here. So today I'm going to be speaking about additive and contaminant results as they pertain to elemental spectroscopy. So when it comes to elemental spectroscopy, I guess we should start with a little bit on the testing. The scope of the test is that it's meant to measure both additive and contaminants as well as wear metals. And the significance of this testing is that by measuring all three parameters, you can confirm if there's any significant wear, and obviously if that's being driven by significant contamination. But the other side of it being measurement of the additive levels is usually there just to confirm that the correct lubricant is in application, not so much that we're measuring any additive depletion. But what I like to detail about this test is the principle. If we understand the principle of the test, we can understand some of the limitations and interferences to this test, which help us interpret the results. So for us to perform an elemental spectroscopic analysis, we have to take a sample of oil and dilute it, and then basically we inject it as an aerosol. We atomize it and spray it into what kind of looks like a flame. Now when the sample enters this plasma, it is ionized, and every element on the periodic table under ionization emits a unique color of light. So what we do is we analyze the different spectra of light and the intensity at that spectra, and that tells us how much of a particular element is present. So the fundamental aspect of this test is it's measuring elemental concentration only. It doesn't tell us about chemicals, compounds, alloys, just the individual elements. So when we go through some of the additives in particular, you'll notice that certain elements appear under more than one additive. This test cannot differentiate where that element has come from. It just tells us you've got so much of that element present. Now to give you a quick visual on that, here's aluminum, tin, and lead. These are all three are wear metals. All three visually are silver metallic type particles. But as you can see on this instrument, when we analyze the different spectra, they are definitely unique. So this is how we pick them out one from the other. The second fundamental thing about this test is generally considered to be only accurate measuring particles in the 0 to 5 micron range. And after about 5 microns, the accuracy begins to decline rapidly, and it basically ends up at next to no accuracy, somewhere in the 8 to 12 micron range. Different sources have different answers, so we usually round that to about 10. What that means is this instrument does not measure particles larger than 10 microns accurately. Now, in the world of additives, that's not a big deal because additives are submicron. But in the world of contaminants, gross contamination may go undetected by this test. So that's why I point out this limitation. If you've got great big scoopfuls of dirt or dust entering the system, it is possible this analysis may yield near zero values simply because the particles are too large to be analyzed within that plasma. Now, as for interferences, because we are measuring within this plasma, any sample that enters the plasma must be diluted before entering. So this helps us turn it into an aerosol. Not all oils or greases are able to be diluted quickly and easily, so we do have to alter the diluent that we use. And one other factor is the water content. It's not that water doesn't ionize within the plasma, but rather that when we have the instrument configured for hydrocarbon-based samples, if we have a highly contaminated sample with water, the plasma wiggles. It basically sputters. And when that happens, again, our accuracy tends to go down. So I just like to point these out so you don't question some of the results that you may get over time. Now, as a quick little visual here, just to wrap up the limitation in that, as you can see, spectroscopy or spectrometry, whichever way you want to say it, is fairly accurate at the small particles, but somewhere around 5 microns, that accuracy begins to decline rapidly. And like I said, that cutoff is somewhere around 10. Now, that's not to say that these particles cannot be measured. They just have to be measured through a different type of testing, like analytical ferrography or wear particle concentration. Those would be able to capture them. Now, one last thing I'd like to say about this test has to do with the precision and bias. But to define precision and bias, I just need to quickly mention to you the terms repeatability versus reproducibility. Now, according to ASTM, repeatability is when everything's the same. It's the same sample using the same method, and it's being tested on the same day in the same instrument by the same analyst. Everything is the same. And typically this is trying to mimic what would happen if you analyzed it twice in a row. So we call this one the as close as possible result. How close could any two results ever be to each other, assuming everything was in your favor? Reproducibility, on the other hand, is a little bit different. While we keep the same method and we keep the same sample, what now is allowed to change, allowed to be variable, is it may be sent to 2 different laboratories, or it may simply be analyzed by 2 different analysts or on different pieces of equipment, or possibly even on different days. So what this is hinting at is what would happen if you reran a sample later? What would happen if you split a sample and sent it to 2 labs? How close could those 2 results ever be? And we call that one the real world comparison. It's kind of realistically, how close should you ever expect 2 results to be? Now, the reason I point this out is imagine you take a sample within your system last month, and then you resample it again this month. If you assumed, and this would be a very poor assumption, but if you assumed that absolutely nothing changed in the last month, you're now taking another sample a month later. So arguably it is the same sample, it's just now being analyzed on a completely different day. Well, this is when we start to see how much difference should we expect as a minimum between samples. Now, when ASTM defines repeatability and reproducibility, one of the other bracketing parts of the statement is they always state that it's generally 19 times out of 20, meaning that the values I'm about to show you are only exceeded once every 20 samples, or about 5% of the results may exceed these. Now, of course, most high production labs like ours wouldn't survive if we had 5% of our results going out the door with less than this accuracy, because that would be a significant number of samples every day. So we do strive to be closer than that. But that is by definition what ASTM allows. So just to quickly show you one value on these 2 charts, look at calcium. Calcium is the 4th row, and look down at the last column on the right. So on the left-hand chart, repeatability of calcium at 1,000 parts per million is expected to be 32 parts per million. What this means is if I analyze the sample twice in a row, it would be expected to be within 32 parts per million, up or down, just the absolute difference between two results, 19 times out of 20. But look at the right-hand chart now, and imagine I take that sample and simply analyze it on a different day or on a different instrument. Now reproducibility jumps up to 120 parts per million. The reason I show this data is to help exemplify when people are interpreting, in particular, additive elements, small changes are expected. You cannot read into most of the changes that we do see on additive elements and say that with any certainty that it's additive degradation or if it's a mixing of products. There is a significant allowance on these values. So I don't expect anyone to use these charts as a reference, but I more pointed out to say to you, look, if the additive element varies by a few ppm, that's nothing. That is insignificant. Even if a trend appears to be there, you'll notice that as you look down other additive elements, that the expected variance between results is greater than 10% most of the time. So the elements that I'm going to go through today are all the ones on the right-hand side here. I'll go through all the additives and I'll go through all the contaminants. So starting off at the top, I'm going to give you the most common cause for every additive element and contaminant element, but then I'll give you some of the exceptions and I'll follow through with some of the pitfalls, some of the misinterpretations that occur. So one of the common denominators you'll see on every single slide about additives is that I'm going to state that you should look for greater than 25% variance before you start to assume that it's a mixing of products. So basically what I'm saying is that if the result is within 25% of the baseline value, usually I consider that to be normal and just move on. So calcium, as an additive, where would you find it? Most commonly it's going to be as a detergent additive. If it does degrade, if it does get consumed, due to its alkalinity, some acids may react with it. One of the things to note is it's still present in the oil sample. And again, this test is only measuring how much is there, not if it's working. So your calcium result typically doesn't change due to degradation. It's still present. Now, what about calcium if it's not coming from an additive? Well, one of my pet peeves in industry is the use of things like kitty litter. Kitty litter is usually sold as some sort of Fluor-Zorb or Oil-Zorb named product meant to help clean up spills. These clay-based absorbents tend to be a clay made from magnesium with a little bit of calcium in it, and they have a bit of an iron contaminant in them which imparts the sort of brownish or reddish color to them. So when I see iron, calcium, and magnesium increasing in a sample, particularly if the particle count's going up as well, I'm fairly certain it's contamination due to this type of absorbent. The use of this absorbent is always on the outside of the lubricated asset, of course, but this clay forms a lot of dust. It doesn't take much disturbance, and it will create dust. And this dust is rather small and will generally enter through most breather technologies. So it does breathe into the system, and it is highly abrasive, so it will lead to future wear. Another source of calcium, and it's always coupled with magnesium, would be hard water. So if there's any condensation occurring within the asset, or sometimes it could be leakage due to a gland seal, or even just maintenance. If equipment is frequently washed down, sometimes water will enter into the lubricating system through the washdowns, but the water may boil off or be driven out due to heat. What will remain, though, are the hardness elements, calcium and magnesium. One last comment, though, could be if you're operating near roads, roads that are salted. Some of the salts that they use on roads in the wintertime are calcium and or magnesium based. When the roads dry out in the springtime, the dust may become airborne and it may breathe into the system. So there are times where we may see seasonal increases. Nothing too dramatic, nothing too damaging, but at least it explains where it's coming from, particularly if you're using an oil that does not have any calcium or magnesium in them and you're trying to explain why there's a sudden increase. Now the pitfall with calcium is that trying to spot calcium as a contaminant, it can be difficult because many oils contain calcium as an additive. Most hydraulic fluids contain a little bit of calcium, maybe 100 parts per million or so. And when we start dealing with engine oils, it's not uncommon to see 1,000 to 3,000 parts per million calcium. So trying to find calcium as a contaminant is going to rely more on the correlation with other parameters on the report, particularly magnesium and possibly the water content or the particle counts. Now, saying that, if we look over to magnesium, this is an absolute duplicate of calcium. There's nothing new I'm telling you on this particular slide regarding magnesium. I'm merely crossing it off the list and just saying, again, we're looking for greater than 25% change to baseline values before we start to consider that there's a cross-contamination of two lubricants. Magnesium is likely to also appear from the kitty litters, from hardness, and from salts. And again, is also masked by the typical levels we see as an additive. So nothing new with magnesium. So I'll just move right along to phosphorus. Phosphorus as an additive is present in 2 out of 3 of the additive technologies. Anti-wear additive technologies always have zinc and phosphorus in them, typically relatively equal concentrations of both. Extreme pressure oils, if they're going to have phosphorus, don't have any zinc associated with them. R&O, rust and oxidation inhibited oils, do not have these same additives at all, so you will not see any phosphorus whatsoever. So phosphorus is kind of a quick check on the oil to determine, broadly speaking, which additive technology it might have. If it's got phosphorus, you know it's not an R&O oil. If it's got phosphorus with zinc, it's probably an AW versus an EP. But again, we're looking for more than 25% change before we start assuming that there's been any mixing of oils. So where would the phosphorus come from if it's not meant to be in the oil in the first place? It may come from grease. Greases, as you probably know, are also additized with anti-wear or extreme pressure additives, and again, they'll use much the same additive technology. So if we've done recent maintenance and used grease during reassembly, it's possible some of it might migrate into the oil. Or if we know that we've got some sealing technology that requires greasing, greasing may leach into the oil that way. In either case, the level of phosphorus is not likely to cause too many problems until it gets very, very excessive. And that's only if the system is designed to run without an anti-wear or an extreme pressure additive. But a little bit of this type of crossover typically is not too problematic. Now, one of the pitfalls with misinterpreting phosphorus is sometimes we see phosphorus after maintenance and we assume it might be something to do with grease or similar. But what it can have something to do with is the industrial degreasers that we use. So if the parts have gone through a parts washer, or if it's something that's stationary and bolted to the floor, if we sprayed it with a degreaser and washed it down, phosphorus may migrate into the oil in this form. Now, in either case, it's not likely to be harmful in the long run, but again, I pointed out just to exemplify why it's there. If you can explain it, you can live with it. When you can't explain it, that's when it gets to be an issue. Now, saying that, the other element that most people concentrate on, broadly speaking, is zinc. Because again, zinc helps identify the broad application. If it's got zinc and phosphorus, we know it's likely to be an anti-wear oil. If it doesn't have zinc, it may be an EP or an R&O oil. So we do expect zinc at times, but most of the time we don't. Most of the EP oils and R&O oils should have 0 zinc in them. So where would we find zinc if it wasn't meant to be part of the additive chemistry? You will find zinc as a wear metal. Now, as a wear metal, it's got a lot of different sources, so we have to correlate what else is there. If we have any yellow metal in the system, zinc may be coming from any brass parts. It's not in any bronze parts, and that's the differentiator. Both brass and bronze contain copper, lead, and tin. What differentiates brass from bronze is the fact that it has some zinc to it as well. Now, when we think of solder, typically we think solder has lead and tin in it, but sometimes it may have some trace levels of zinc. Solder may enter into the lubricant if it's leaching in due to a high acidity, so typically this correlates with a higher than normal acid number. If we've got galvanized steel tanks or piping, the galvanization as it wears off will release zinc into the oil. This should correlate with some levels of iron. Lastly, coatings. If we have chrome coatings on parts, it's not necessarily strictly chrome. Often the chrome is coupled with a little bit of nickel and probably a little bit of zinc. It helps with the corrosion properties. Now, all of these sources here typically will correlate with other wear metals because there's going to be more than one. Which of these is a possibility? One comment I'll make, though, is that it comes with the pitfall that most of the applications that would have any of those sources are likely to use anti-wear based additive technologies, meaning that you're probably going to find several hundred ppm of zinc present as an additive. Therefore, it's going to mask seeing it as a wear metal. So the correlations become paramount in identifying potential sources of the zinc. Now, moving along to some of the less common ones, the ones that aren't necessarily looked at. Barium. Barium was used as an additive in North America, but now it's been pretty much banned and you don't see it being used in too many products anymore. So this is one that most people typically ignore because they don't have any in their baseline values and typically don't see it coming across in any used samples. But if you're going to see it, likely it's coming from grease. Barium is not an additive in grease. It's actually one of the thickener systems that we might use. I mean, lithium is by far the most common thickener system in North America, but barium is a possibility. And, you know, some of us purchase assets from different parts of the world, and then sometimes they come with an OEM grease. Might not be a lithium-based grease. It could be a barium-based grease. So barium's not typically found, so when we do see it, we should probably pay close attention to it because this means something unique has entered our system. Now, the pitfall with barium is sort of along those lines. It's one of those things that's hardly ever there, hardly ever checked. So therefore, I'm saying if you see it, we should investigate. Try and figure out why it got in there. Now, moly or molybdenum is used as a friction modifying additive. This is typically found in engine oils. It's not found in too many other products. So we do expect it in some products, but many products you probably never see any level of moly present. So this begs the question, why do we see moly in some systems? Well, if it's a reciprocating application, if it's a compressor or an engine, ring technology has switched away from the chromium-based metals that it typically used, and we're now seeing other metals, particularly things like molybdenum. So as we experience greater wear, we will see a proportional increase with molybdenum and iron. And this would indicate to us that we've probably got some sort of alloyed part wear. If it's a disproportional increase between moly and iron, moly rising faster than the iron, this typically indicates a ring cylinder or reciprocating type wear. And the reason why moly would be increasing at a faster rate, not necessarily at a higher level, but at a faster rate than the iron, is because moly is the more sacrificial metal in this case. It's the one that's expected to wear. Now, the pitfall with moly is rather unique. There was a time when those that rode motorcycles would always be concerned about whether or not moly was present in the oil, because many motorcycles come with a wet clutch application, and wet clutches do not want to see friction modified oils in them because that would prevent the clutch from engaging. So the common go-to was to look at the API donut, and as long as the bottom half of the donut was blank, like the one I've got pictured there, it was a safe assumption the oil was not friction modified because it was not energy conserving. Well, one thing about the API donut that has changed over time is we don't say energy conserving anymore, we now say resource conserving. And to qualify for resource conserving isn't merely the use of a friction modifier additive, it is also coupled with an increase in fuel efficiency. So it is possible that there are some oils out there that are additized with a friction modifier but do not achieve sufficient fuel economy increases to warrant being given the rights to publish resource conserving in the bottom of the donut. So what this all amounts to is that the assumption that a blank bottom half of the donut is not friction modified is no longer valid. So if you're concerned about the presence of moly in an oil and don't want it, then you're best to look at the application for the product. And if it doesn't openly state it's suitable for motorcycles or specifically suitable for wet clutch applications, it's probably safer to assume that it has a friction modifier and that the oil should probably be avoided. So that's moly for you. Now moving along into the contaminants section, the first one we have is silicon. Now silicon, I state, is coming from dust and or dirt. There's actually quite the difference between these two products. A little story I like to tell here is if you've ever heard the saying, red sky at night, sailor's delight, red sky at morning, sailor take warning, then you're actually somewhat aware of the difference between dust and dirt. You just never realized it before. Those of you who live near water probably appreciate most sunsets take on a yellow to an orange color. They're actually not very inspiring. But any of us who live near prairies, farmers' fields in particular, might notice that while the farmers are out working, we get some glorious sunsets. The reds and the purples, it's sort of like the ending scene of Gone with the Wind, when tomorrow shall be another day. Beautiful, beautiful sunsets. The difference between these sunsets has everything to do with what is the contaminant concentration like in the atmosphere. As the sun sets and it takes on a different angle, it reflects off the contaminant particles in the sky. Now, we always have dust in the air, silicon dioxide. It is a breakdown product of quartz and sand. This is always present, so sunsets always have a yellowish to an orange color. When they start to take on the much darker colors, the reds and the purples, this is when we have actual dirt in the air, and dirt, like topsoil earth, is aluminum silicate. It is a completely different mineral. It can be evidenced on an oil analysis report as having a roughly 3 or 4 to 1 ratio between silicon and aluminum, meaning silicon is the higher value. Reason I point this out is that we expect dust. Dust is everywhere. There's nowhere on the planet we don't expect dust. Dirt, on the other hand, takes greater effort. And going back to the red sky at night saying, the reason that saying exists is if we have a red sky at night, it indicates stronger winds coming from the west. So that's where the saying comes from, and that red sky in morning, sailor take warning, is because the sun rises in the east, and that indicates higher winds to the east of us, which were generally considered to be less favorable sailing winds. But what the saying is representing to us is that it takes higher winds. It takes greater disturbance to put dirt into the atmosphere so that it could be breathed in by lubricated equipment. Dust you're never going to escape, regardless of the asset's placement. Dirt, on the other hand, you don't expect. So when we start to see not just silicon, but silicon with some aluminum, that indicates a greater source of contamination, either more disturbance around the asset or a bigger point of entry, because dirt is generally a larger piece of particulate than dust is. So understand the difference between dust and dirt. They're often used synonymously, but they are in fact two completely different types of contaminants, and the presence of one over the other may indicate a far more serious problem. The other thing to note about the presence of dust or dirt is that do remember when we're measuring this test, it is analyzing within that 0 to 5 micron range typically. So we may see high levels on this test that do not correlate with other tests such as particle count. When we see an elevated particle count in conjunction with elevated silicon values, what this is telling me is I've got both large and small particles in my system. If only the elemental spectroscopy is high and particle count is low, it means I likely only have small particles, and that's generally considered relatively normal. If my elemental spectroscopy is low, but my particle count is high, then that tells me I've only got large particles in my system. And that may present itself as a much more serious problem, or Oftentimes what those of us in the lab will consider is it was merely a poorly taken sample. If we see what we call the anomalous silicon, high silicon without any associative wear metals, we ask ourselves, how could all this abrasive silicon be there and there not be an increase in wear? Generally speaking, we assume then the silicon entered into the oil sample after it exited the component. So if you don't wipe down the area around the sample point, if any debris falls into the bottle or gets onto the cap before you close the sample up, it will show up as elevated levels of silicon in the sample. Doesn't necessarily mean there's a problem. Just means you need to take better samples. Now the exceptions of silicon. Those of you who use a silicon gasket maker, any form of sealant like that, you may get silicon in there from the sealants. Now this silicon tends to dissolve into the oil. It doesn't tend to be abrasive, doesn't tend to cause any problems. So it's not an issue that it is there, but this merely helps explain why it is there. Also, again, going to greases. Greases can contaminate oil systems. If you're using a silicon-based grease, which is sometimes used in sealing applications, you may get some grease migrating over into the oil side. And again, you will at least be able to explain why it's there, but it's not necessarily going to indicate any problem exists. Now, the pitfall with silicon, again, just to reiterate, look at the size of the particles we're measuring. Elemental spectroscopy is small, particle count is high. So you might not see the correlation, but whether or not you see the correlation and how that correlation exists will help guide you as to the severity of that problem. The other thing I like to point out, though, is decreases. When people take samples over time and when they do not change the oil, you expect the values to slowly increase in relation to the time or the service on the oil. There may be times where this number plateaus, and despite additional service or time on the oil, the number stops climbing. Now, some people get excited about this and say, great, it's not getting any worse. I take a rather pessimistic view of this and try and explain away why that may not be the correct answer, and I start looking for different answers first. Basically, I use the guilty till proven innocent approach. So if I have a level of silicon that is suddenly plateauing and no longer increasing, what I assume until I can prove otherwise is that the size of the particles has grown. My contamination has gotten worse and has now gone outside detection range, meaning that I can no longer measure them accurately, so they're not showing up as an increase anymore. So I seek to identify that first. So I check things like breathers, dipsticks, fill caps, hatches, whatever exists as an opening into the system, and see if perhaps this is damaged, not properly put back into place, or any other issues. The other scenario that might exist is if you only take samples at drain and you have relatively consistent values with consistent drains. Again, you might see over time whatever the level of silicon might be, and then suddenly you have a sample and it's significantly lower than history. Again, I don't take the view that it got better or that the leak fixed itself or any of those scenarios. I again assume that perhaps it's much worse, and I seek to prove otherwise before passing along that report. Now, moving on to boron. Boron is present as an additive in some fluids. It is there much like calcium and magnesium are there. It is used as a detergent additive. But I will say this, in much lower concentrations than calcium and magnesium are typically seen as. So we don't always see boron in oils, but it may exist. Where we do get concerned when boron exists when there shouldn't be any boron is that it is a good indicator of a coolant leak. So if you have any cooling system attached to the lubricant system and there's any way for the oil and the coolant to mix, whether it's through tubes, a radiator, any form of gaskets, then this becomes a possibility. And why the boron exists is that these glycols that we use are not very anti-corrosive naturally. They have to be additized to properly protect the metals. So the inhibitors that we use in these coolant formulations, coolant being a glycol water additive mix, Some of them are borate based, so they show up on the report as boron. Now, quite commonly, we also have sodium and potassium as well, so you'll often find at least 2 of these elements being present in a sample if there is a coolant leak. One of the things to note about a coolant leak is that though coolant is largely glycol and water with only a little bit of additives, the glycol in the water may actually boil off or be driven out by combustion processes if it happens to be an engine. And if you look at the rest of the report for a glycol content or a water content, you might find there's next to nothing there. Don't assume then that that puts you free and clear of a possible coolant leak. The water and the glycol may boil off or be driven out, but the additives will remain in the oil. So when we see levels of boron, sodium, and potassium, we're pretty certain that is a coolant leak, even if there's no other evidence. Now the pitfall with boron, and some of you may have noticed this before, but if you purchase lubricants from a company that recycles their drums and totes, there are times when you might open a new tote in particular because they're made with plastic, or a drum if you use plastic drums. And upon opening the drum, one of the first whiffs of odor you get out of that drum reminds you of a hospital. At least that's what I think it smells like. These are the borate-based cleaners that they use when they steam clean lubricant-containing vessels to try and clean them out completely so they can be reused. So there are times where we've had customers who've had trace levels of boron appear in new oils that typically weren't there before, but were traced back to be right from the new oil container and not just entering the asset. Well, what it is it's residual cleaner from some of these cleaning processes, and again, it's not going to cause any problems, but at least it can explain why it's there. Now, lithium is a pretty quick one to cover. The only reason we would ever expect lithium in a sample of oil is because there is grease in the oil. As you heard me say earlier, lithium is the most common thickener technology for greases in North America. Nearly 3/4 of the greases that are sold in North America are lithium-based. So when we see lithium, that is typically why it is there. I can't give you any exceptions or pitfalls that make logical sense outside of being process related to unique applications. So when we see lithium, that's the most common thing we're going to look at. But again, it doesn't necessarily mean there's going to be a problem, it just helps explain why it's there. Now sodium, as you heard me say earlier, sodium is expected to be there as an indication of a coolant leak. We don't frequently use sodium as an additive element anymore, but we do use it as an additive of coolants. So when we see sodium, we do expect that to likely be caused by a coolant leak, remembering that it may be there with boron and or potassium as well, but it doesn't necessarily have to be there with the glycol or the water content. Those, again, may be driven off by the temperatures that it's operating at. Now, where else sodium could come from? It could be salts. Of course, if you're located near roads that are salted or located near salt water, then it becomes airborne. It can breathe into the system, particularly once it's dried out. It's very readily airborne. It will enter the system, may or may not cause an increase in particle count, depends how large the particles are, but it will help promote some corrosion. So you may see levels of aluminum increase because sodium really hates aluminum. When it comes to elements on the periodic table that don't get along, zinc hates sulfur. Sulfur is often used in EP additives. Sulfur hates copper, and sodium hates aluminum. So there are some unique combinations out there that when we see one, we kind of expect the other because we know there may be a reaction taking place, this being one of them. You may see increases in the acid number as well if that's being measured, but you will see the corrosion. You will see a lot more aluminum appear all of a sudden. Now, for those of you who work in particular in the power gen industry, one of the common filtration technologies that exists out there is acid scavenging. And acid scavenging can use 3 different technologies, quite commonly Fuller's Earth being one of the older technologies out there, and ion exchange being one of the newer technologies. The one in the middle is what we refer to as activated alumina, or by product name it tends to be called Selexor, being the most popular brand of the product. But it is a sodium and aluminum based white powder. And as a powder, it sort of is halfway between salt in terms of size of particles and icing sugar. So there is some portion of it that is as fine as icing sugar and will enter into the lubricating oil system because it has exited the filter that it is supposed to be contained in. Now this will show increases in sodium and aluminum. At first, this is not an indication of any significant problem other than some leaching from the filtration, but over time it may cause metallic salts to be created. So this, in the long run, will definitely yield future problems, but you can probably deal with it at its earliest stages if you have slipstream filtration and can get to a very fine micron rating. You can usually knock most of it out. So understand that it is very small. It may not correlate with a standard particle count because that's measuring particles 4 microns and larger. If it shows up in oil analysis under elemental spectroscopy, is definitely under 5 microns. So you're not going to necessarily see all of it through one test. You'll need both tests to confirm that you've got a broad application of it in there and perhaps even have a filter failure. Now the pitfall with sodium is that not all formulations of coolants contain sodium-based inhibitors anymore. One of the ones that exists out there is a Honda. A Honda automotive coolant is a sodium-free formulation. So you're not likely to find a coolant leak in this type of vehicle by looking for sodium. You'd have to rely on some of the other elements, in particular boron. So do be aware that there are times when the old standbys of seeing sodium and potassium in a sample identifying a coolant leak may not hold true anymore, and it's not because the leak doesn't exist, it's because the coolant doesn't use those types of additives. Now potassium being the other half of the common coolant additive, we do expect potassium to be present when there is a coolant leak, so this is no new information here. But I'd like to tell you a quick little story. I did have a client who did not send samples to the lab very regularly. They only sent samples to the lab if they failed a screening test done on site. Now the on-site screening was a portable particle counter and a hot plate. And they sent a bunch of samples to the lab one day because they said they all failed. So they wanted us to confirm the failure. Well, when we analyzed them, one of the tests we did on them they weren't doing was elemental spectroscopy. And lo and behold, all the samples showed elevated levels of potassium. We confirmed the particle count was definitely high, so they were concerned that the potassium that we found with the particle count they already knew about were somehow related. So this was very early in my career, and I was asked, where did the potassium come from? So I quickly said, coolant. Well, they indicated to me these were all hydrostatic gearboxes. None of them had a cooling system, and in fact, they had no system with a cooling system on site. They didn't even have coolant on site, so this was not a possibility. So I was scratching my head, and then I thought, oh, bananas. Now, some of you might laugh at the thought that I would suggest bananas had contaminated an oil system, but I kid you not, it is an old millwright type trick to throw banana peels into a gearbox and helps quieten it down. Now, the chance that every gearbox on site had a banana peel in it, relatively equal concentrations, was remote. So my client said it's probably not bananas. So at that point, I was stumped. But we were friendly. We'd spoken on the phone several times, and he lived significantly north of where I was located. And he asked me, he says, hey, has the forest fire hit you yet? The smoke from the forest fire. And I said, yeah, actually, just this morning I woke up and it smelled like a forest fire. And that's when the light bulb went off in my head. I realized that he had been spending many, many days in a cloud of smoke. So I phoned up the environmental body at hand and asked them if they'd done an air quality study on the forest fire smoke. And they answered, no. Why? Are you concerned? Which I thought was a very odd reply. I was wondering if I should be concerned, but the long and the short of it was that they were able to provide me with an analysis of a previous forest fire, the smoke from the forest fire, and As it turns out, if you burn wood or coal, you will release potassium into the atmosphere. So I know this sounds like a bit of a remote possibility to some of you, but hear me out. All you have to do is be in the fallout zone. You don't have to be within sight of it. You don't have to necessarily see it or smell it. You just have to be where the dust emitted as smoke settles. So this particular forest fire that triggered my knowledge of this source of potassium was actually occurring just north of Whitehorse in Canada. So way up, practically within sight of Russia, and the smoke traveled all the way down to Colorado. So it covered the Rocky Mountain chain for the greater part of the Rockies. I mean, smoke can distribute over a large area. Now, the pitfalls with potassium, just to reiterate, again, not all formulations of coolants have potassium-based inhibitors, much like I said about sodium, so you can't count on specifically knowing that there is going to be potassium in all coolant leaks. The other pitfall, as I pointed out, is you don't have to be within sight of the smoke. The graphic that I've got there, that was the fire, this was just over a year ago, occurred in Fort McMurray, Canada. It was a massive one in the oil sands, so this is where Canada gets most of its oil. It was a fire that decimated the town. Half the town went missing, burnt to the ground. But look at the fallout zone and look at where the concentration is. There was actually a gap between the source, which is up in the top left of the picture, where there was no fallout, where the fallout was very light. But the greater fallout actually occurred all the way down to Washington. So though this fire was not within sight, and you might not have smelt it in the morning like I did that one day, you might live in that belt of red there and know that you were in the greater fallout zone. The other example I quickly give is that, remember the volcano with the unpronounceable name in Iceland, just outside Reykjavik? The fallout zone for that volcanic ash was pretty much all of Europe. So we can explain why we see certain elements in some of the applications, at least some of the time. So in summary, I have also provided these two tables. So this table here is a list of potential sources for elements, assuming they're a contaminant. So I haven't given the sources of aluminum as an example as a wear metal, but I'm saying if aluminum's there and it shouldn't be there, where did it come from? So I've reiterated, dirt as the one source, and again, as a thickener technology is yet one more. So as you can see from this chart here, there are some sources that are on things I did not cover within this presentation, but I merely provided as extra information. The last table I have to show you is this one here, and it's a potential source of the additives. And again, it's assuming that this element is supposed to be present as an additive. So you might see a couple things on this list that you would have thought belonged on another list, like you might have thought copper was a wear metal, or you might have thought silicon was a contaminant. But I'm saying to you, if copper is used as an additive, what kind of additive should it be there as? And if silicon is used as an additive and not, confirmation of dust contamination, what type of additive should it be? So both charts are there for your reference at the end of this presentation. And with that, I'll open it up to any questions anybody's got. So I'm seeing one question here. It says, I use the same oil on all of the equipment. Why do some have a number on the calcium line and some have no number on the calcium line? There could be more than one answer to this one here. So the simplest answer to this should be identification. It's logistics. Check the reports and ensure that the reports absolutely do list the same oil on both different reports. Because as long as we've got the oil identified, we automatically fill in that baseline information column. If the oil is identified differently, on the other hand, and by differently, I mean it could just be same brand, different grade, or it could be that it's given a more generic name. If they are, in fact, different in any way, we may or may not have a baseline reference tied to that particular name. So I'm saying it's an administrative or a logistical issue when you have what you would consider to be the same oil in two different assets and only one of them's got the new oil information. The only other reason that that would occur is, again, it's not necessarily administrative on the side of the end user. It could be something more on our end, meaning that the way you've identified it helps us align it to a new oil that we do have, and some people might have identified it in a way that doesn't align with the new oil that we have. So if you point these kinds of things out to us at any point, just give us a call, send us an email, and say, hey, this machine uses this oil. We can reissue the report with the new baseline information on it. That's not an issue at all. But if we don't have a new oil reference for it, we can't populate that baseline column. We require samples from end users to be able to do that. All right, just looking to see if there's any other questions. There's one here. We'll just open this up. It says, for the potential additive sources, are these for only particles that are 0 to 5 microns, or can the potential sources be used to explain larger particle counts as well? Well, kind of a little bit of both on that answer. These charts are in specific reference to elemental spectroscopy. So the intention is that, yes, they're going to explain the 0 to 5 micron particles primarily. But obviously, if you look at some of the sources, they may exist in particles larger than the 5 microns. So they can, to some degree, explain an increase in particle count. But a particle count, to be fair, is merely a count of the number of particles, hence its simple name. It doesn't identify what the particles are. So you may assume it or presume it from that particular chart, but that's not necessarily going to be the only sources or necessarily the accurate sources. So kind of yes, kind of no. Another question says, are there incompatibility issues on some of these additives? For sure. That is a definite. Basically, when I talk about additives, I say this quite simply. Additives fall into two categories. There are additives which are active on metal surfaces, and there are additives which are active within the fluid. If you think about just the first group, the ones active on a metal surface, I have things like extreme pressure additives, I've got rust inhibitors, I've got detergents, just to pick three broad groups of additives that are all active on the metal surface. Now, while these three additives are not necessarily going to be incompatible in terms of that they react with each other or have a negative synergy or anything like that, one of the bare bones minimum things that is going to occur is because all three additive technologies require a bare metal surface to be active on. If you use more of one than another, you're displacing the opportunity for these other additives. So when you take a fully formulated product that, say, does not have a rust inhibitor, and you suddenly introduce a rust inhibitor to it, the rust inhibitor is going to, what I call, vie for the real estate. It's going to try and find some metal to bond with. And you're going to upset the balance with your detergents that already have an expected view of how much real estate is available to them. So in the bare minimum, when you start mixing some of these additives that aren't part of the original formulation, then you're going to be upsetting the balance of performance. At times, though, there will be, in fact, negative synergies. So not only can you assume that there may be fighting for the real estate, even if you said maybe there's room for everyone, sometimes the presence of one will reduce the efficacy of another, and that would be considered to be a bit of an incompatibility. Worst case scenario, yes, some of them might mix with each other and actually cause a very negative reaction, meaning that it might displace one completely or react it out or something like that. But understand all those incompatibility issues are taken into consideration in each individual fully formulated product. So as long as you've got them present from one product, no, there's not an incompatibility issue. The question only arises if you have more than one product being mixed. Another question says, how can you distinguish silicon in oil as antifoam from dust? By this test, you can't. That's the point. This test only identifies silicon as an element, not silicon as a compound alloy or chemical. So the way that you would distinguish it from dust is actually rather simple. If you send in a new oil sample for baseline testing, that's the level you expect to see there as an anti-foam additive. And I'll tell you this, in my experience, this is like 2 or 3 parts per million. This is never that much, really. As soon as I start seeing numbers like 10 parts per million or higher, that's probably coming from some outside source like dust. So you can, to a point, differentiate them, but you are making an assumption. The test does not outright identify the difference between the two. It merely identifies the level of silicon, all silicon. Another question says, is there an action level for contaminants? Well, I don't like to ever give a single number because that has way too many variables built into it. Time on the oil, type of machine, type of environment, et cetera, et cetera. So no, there's no level, there's no number I like to give. I like to just point out the trend. There is a normal level of contamination that should be expected under normal operating circumstances, and that will, of course, gradually increase over time on the oil. So without an oil change, the level of contamination should constantly climb. If that rate begins climbing at a faster than normal rate, that's your action level. If you only take samples once per oil drain, then you probably established a relatively normal level, and if it's ever significantly higher than that level, again, that's probably actionable. But no, there's no single number I can give you, right? Some systems might operate at 10 parts per million is considered excessive, some might be 50, some might be 100, and one of the greatest variables to where that number sits is the volume of the system, because all these numbers are measured as a concentration, not as an absolute quantity. So always keep that in mind. So no, there is no action level, and I wouldn't want one. I wouldn't want to rely on that one. I think I have brought myself to the top of the list. Let me just go back down to the bottom of the list and see if any new questions have come in since I started answering them. Okay, there's a new one here. It says, would the oil drum have the list of additives on it? Long and short answer on that one is no, never. No product data sheet would ever list the additives, and even if they suggested what additives were present, like saying it had a detergent or an anti-wear additive, they're not going to tell you what elements to expect nor at what levels. So no labeling of any oil container is ever going to provide you with significant guidance as to what to expect. Where you may find it, on the other hand, is on the product data sheets. Sometimes there are lubricant suppliers who will list this data. It is a bit rare. Where I go to help identify it, though, is the safety data sheets. There they sometimes list out the types of additives that will be present. But safety data sheets are allowed, they have an allowance anyways, to not give away anything proprietary, so they probably will never give you very precise concentrations. So you're never going to get a good solid answer as to what's in the oil until you send in a sample as a baseline and have it tested. No literature is likely to provide you with that unless the lubricant supplier offers some type of oil analysis with their program, and then they've probably got a database of them and might provide them to you. It's not uncommon, but it's not the default answer. Another question says, we mineralize our oil grease in a microwave oven. So I think we have all the particles even greater than 5 microns. We do not inject with a solvent. If you perform what's generally referred to as digestions, quite commonly in the soil testing industry, they take solid samples of soil and analyze them with the same elemental spectrometer that I've just described, then yes, you are capturing particles larger than the range I've described here. I have just given the sort of common view of what most commercial labs do. It allows high-speed production, simply dilute and inject, and away you go. As for the microwave technology, you'd have to check the method on that one to see what it suggests as the cutoff. Another question here says, what other additives cause high acid number aside from anti-wear, zinc, and phosphorus? Most additives are actually alkali rather than acidic. So when we think of most of the detergent type technologies, those ones are likely not to contribute significantly to the acid number. Ones like your extreme pressure and anti-wear ones will contribute partially to that acid number. So that would be the ones I would probably focus on more than any others. Beyond that, most of the other broad common additives don't contribute significantly to the acid number. Another question says, what are the methods on how to remove undesired additives? That, I can jokingly say, has a pretty simple answer. Change the oil. I know that's probably not the answer you're looking for, but to try and remove any one single additive out of a mixture of additives is a near impossibility. How to strip all additives out of an oil while retaining the oil can be done ionically. You can use ion exchange resins, ion charge bonding, whatever you want to call it, and they may ionically be removed, but you're not going to remove them with mechanical filtration, and it is very difficult to be selective with most additive technologies. So if you have additives you don't want, usually you're forced to bleed and feed or outright change the fluid to what you do want. Like I said, very difficult to be selective. Another question says, is the interpretation of ICP results for greases completely different than oils? No, I tried to keep this presentation kind of balanced that way, point out oils and greases. Again, from an additive technology standpoint, the additives in oils are quite similar to the additives in grease. So that part holds up true. And then, of course, contamination is just contamination. So there's no differentiation within the contamination section. Although I don't expect, a grease application to have a coolant leak, as an example. That would, just logistically not be a common thing. But hey, if it could happen, it could happen. So another question says, in oil analysis used, is there a more precision way to establish oil limits, absolute or statistical? Again, I'm not a big fan of establishing numerical limits. But if you're going to do it, yes, statistical is probably the better way, looking at what's normal for that type of machine or a group of machines, a fleet, and statistically arriving at them. There is actually an ASTM standard for doing that. Basically, it works on standard deviations. Anything within one standard deviation is considered absolutely normal. At 2 standard deviations, you set your first warning limit, and at 3 standard deviations or higher, it's considered in alarm. That's one way of doing it. I prefer just basic trending rather than worrying about setting alarm limits all the time, because, hey, every time you change an additive chemistry, a formulation change, if there's a mixture of products, if you change an operating parameter, right, every one of these variables will start to skew that original calculation. Another question on it says, when you have an EP oil with sulfur and phosphorus, is it normal that the number doubles sometimes? No. Additives should never increase on their own. If they increase on their own, it is indicating that a other product is likely contaminating the system, or that some type of reaction has taken place. When it comes to EP additives, these are renowned for being able to form acids quite readily in the presence of water. So as we see an increase in water content, we will see an increase in acid number content. But, the law of conservation in chemical reactions indicates that the level of sulfur and phosphorus isn't going to change because it's altered its form from an additive to an acid. So, like I said, if it increases, it's because there's some other reaction beyond what is the normal expected reaction over time. And that is the last question on my list. And we've arrived at an hour, so at this point I think we're probably best to stop it for now and answer any other questions offline.
Thank you, Evan. You did a great job. I see a lot of people also sending their thanks, and I have received a couple private emails as well. So thanks again, Evan, for a great webinar. As I mentioned, everyone, via the chat, I'm going to be sending out the recording and PDF of the slides probably in about an hour or so. Thanks for joining our webinar today. Thanks, Evan.
All right, thank you.
Bye-bye.